Whether you are navigating across the country or through a wilderness area, knowing where you are and where you are going is very important. Now that there is so much mapping technology, it can seem like we can retire our understanding of maps, but this is still a critical skill. First, the more you know about mapping, the more you can do with it, and the safer you will be. Second, you might actually have to use those maps someday when technology is not working or it does not do what you need it to do. Yes, there is a lot that digital mapping can do, but there are still tasks that can only be done with good old paper, compass, and know-how. A map is a graphic representation of the physical features, natural, artificial, or both, of a part of the whole of the Earth's surface by means of signs, symbols, or photographic imagery at an established scale, on a specific projection, and with the means of orientation indicated. So how do we take a mostly round object like the Earth and create an accurate flat map? The first step is to create a spheroid, a perfectly smooth surface that aligns closely with the surface of the Earth. For North America, the spheroid of choice is the Geodetic Reference System 1980, or GRS 1980, on which the North American Datum 1983, or NAD83, is based. North American Datum 1983 is tied to the North American tectonic plate. Satellite data has helped us refine our measurements for a new spheroid that is based on the Earth's center of mass. The World Geodetic System of 1984, or WGS 1984, uses the Earth's center of mass as its origin. When originally published in 1986, NAD 1983 and WGS 1984 could be considered aligned. Because of tectonic movement over several decades, locations measured by the two different datums will be a few meters apart. Now that we have a smooth surface, we can divide it up into marked sections. There are several systems that we frequently use for orientation. Check out the videos for Latitude and Longitude, Universal Transverse Mercator, or UTM grid, and the Public Land Survey System, which uses township, range, and section, to learn more. Using our smooth surface, we can project a flat map. There are dozens of map projections, and all have some distortion. The area of least distortion will be the section of the two-dimensional plane touching or intersecting the globe. Each projection has its advantages. Planar projections project the surface of the globe onto a flat surface. The projection point can be gnomic, or from the center of the globe, stereographic, or orthographic. Cylindrical projections wrap the two-dimensional plane around the globe into a tube. The tube can be turned in any direction. A cylindrical projection, where the area of least distortion is the equator, is called the Mercator projection. Check out the video on the Universal Transverse Mercator grid to see how this projection is used in an interesting way. Conic projections place a cone where it is touching a globe, called tangent, or cuts through a globe, called secant, and then flattened. The Albers projection is an example of a secant conic projection. The distortion is lowest at the standard parallels and increases with distance from the standard parallels. The map projection commonly used online is the Web Mercator projection, which can be found on online maps such as Google Maps, Esri, and MapQuest. Other than being generally interesting, this information will serve you in a couple of ways. 1. When you are given a paper map, there is a datum at the bottom. If your map has one datum and someone you are working with has a map with a different datum, you might end up with slightly different readings on a location. 2. When you are working with digital map layers, you might put a feature like a waypoint on a map, and it will show up in a different location if the base map is in a different datum. It's true that for most general users, this concept will not affect you very much in this digital age. However, it is important to keep it in mind when you are working with maps, and it will help provide a good foundation for understanding the different systems we use to communicate location.